Hi, and welcome to lesson 7.3, use similar right triangles. So in this lesson, we are going to look at a few different theorems and a couple different concepts and the idea of a geometric mean, going back and looking at the idea of an altitude, the refresher on hypotenuse and legs of right triangles, and then mainly the idea today is going back and using proportions to solve these similar right triangle problems. So the first theorem we're looking at today is theorem 7.5, which states if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. So if we look at the diagram there, triangle CBD is similar to triangle ABC. Then triangle ACD is also similar to triangle ABC. And triangle CBD is similar to ACD. So in this relationship, the two triangles formed are similar to the original and to each other. And then a reminder of the definition of an altitude. Altitude is simply a segment from the vertex, so any vertex, to the opposite side, and it meets the opposite side at 90 degrees. So typically we think of an altitude such as the height of a triangle. So when you're looking at this diagram here, our altitude would be CD. Goes from vertex C to the opposite side AB and meets it at 90 degrees. So example 1 simply asks us to identify the similar triangles in the diagram. So the thing to make sure that you do when writing a similarity statement is that you match the corresponding parts or vertices. So for example, if we are thinking this bottom side of the big triangle, or top side in this case, is RS, so the big triangle would be RS, we would have to match that up with the corresponding sides of the other triangles when we are naming them. So you have to be careful to match up corresponding parts with corresponding parts. So when we name these, if you just start with any triangle, so in this case, I started with the little triangle here, TSU. So I had TSU right here. Then I knew U was my 90-degree angle. So when I'm naming another triangle, this U is going to match up with whichever letter is the 90-degree angle. So then if I was going to start to name triangle, let's look at RTU in this case. The U in my original 90 degrees matches up with the 90 degree on this RTU, which also is U. So because U came third, U has to come third. Then S on this triangle was on the shorter leg. So then when I look at the other bigger triangle, what was on the shorter leg would be T. So T and S match up. And then R on the new one matches with T on the original. So you just have to match up the corresponding vertices, meaning you might have to turn these shapes a little bit. Then if we're matching up corresponding parts again on the last one, you can compare it to the one in the middle or the original, and then that would line up. On the original, T matches with R, S matches with S, and U matches with T. So example 2 is a visualization and putting together a couple different steps based on this idea. So in example 2, we have a word problem dealing with depth of a swimming pool. So the diagram shows a cross-section of the swimming pool. They want to know what is the maximum depth of the pool. So you can see with this pool, they already gave us a depth of 48 inches. And then to figure out the maximum depth in this section, it was based on similar right triangles. So what I did first for step one was I wanted to identify the different similar right triangles in this diagram. Then when I pulled them out, I also turned them so that I could match up the corresponding parts just to make it a bit easier on myself. So one triangle that I had in this diagram was triangle RMT. So I pulled that out, labeled what I knew, and then moved to the next triangle. The next triangle I looked at was triangle TMS. So we're looking at the smaller one here. I turned it to match up the corresponding parts and labeled my sides. And then the larger triangle, RTS, down here, the bigger triangle around the other two. I also pulled that out and turned it, so all three, it's easier to visualize the corresponding parts. So in step two, how you use the corresponding parts, we know any similar triangle is proportional. So in step two, we want to set up a proportion. So in this case, what we're trying to figure out is the H right here, which is that missing part of the depth. So I know in my proportion, I want H to be in one of the blanks, and the other three parts I want to be built out of info I already know. So if I'm looking at the triangles, I'm going to use triangle TMS here and triangle TRS here. The reason that I'm using those two on triangle TRS, I know all the sides, so I definitely can fill in the info. And then the other one, I could have chose one of these two triangles as long as I was setting it up to solve for H. So matching up corresponding parts, TM on TMS corresponds with TR, and then on bottom, ST corresponds with RS. So I took this leg and then that hypotenuse. Then to solve any proportion, cross multiply and divide. So 152 times 64, divide by 165, and H is approximately 59 inches. So then to answer the question, we have to take the 59 inches plus the 48 that was already there, which gives us a maximum depth of 107 inches. So in example 3, they want us to identify the similar triangles, then find the value of x. So in that first one, triangle EGF is similar to triangle GHF, which is similar to triangle EHG. Then picking my proportional setup, again, I know I need x in there, and then I want to match up other parts that I know. So in the bigger triangle, I can pull the 3 and the 5 for side EG over EF. And then on the unknown, smaller triangle, GH over GF. Cross multiply and divide. So 4 times 3 is 12, divided by 5. So x is 12/5. Then on number 2, triangle LMJ is similar to triangle MKJ, which is similar to triangle LKM. Then we have to set up our proportion. So in this case, matching up corresponding parts and what we know, my proportion would be LM over KM equals LJ over MJ. That would set up as 5 over x equals 13 over 12. Cross multiply and divide, and x would be 60/13. Now we get into the idea of a geometric mean. Now, a geometric mean is used for a few different things, and there's actually a couple ways we can calculate it. But in this case, we're going to define the geometric mean looking at two numbers, a and b, so that it is a positive number x, such that a over x equals x over b. We're going to look at that setup related to some of the triangles below. I'll tell you right now on page 451, there are 3 examples about different geometric mean setups with similar triangles. I could only fit one into the notes, so you would want to go, and there's 2 other examples on page 451 after this one that you'll want to add to your notes. But geometric mean, the geometric mean of two numbers, a and b, is a positive number x, such that a over x equals x over b. So we know in triangles ABC below, it tells us altitude CD forms the 2 smaller triangles, so that triangle CBD is similar to ACD, which is similar to ABC. So one setup here, looking at how the geometric mean can be used in this idea, is we know we want to use the same number on bottom of the left and top of the right, or so the same number or the same value, same distance in this case. So in our setup, the left-hand side, we could look at it as, and this is triangle 1, triangle 2, triangle 3 based on Roman numerals. So one setup would be the length of shorter leg in triangle 1 over the length of shorter leg in triangle 2. So that could be BD over CD. Remember, legs are the sides that meet at 90 degrees. Then on the right, we can use the longer legs. So the length of longer leg in triangle 1 over the length of longer leg in triangle 2. That would give us CD over AD. That way, what that tells us is the geometric mean in this scenario is our altitude CD, because you can see BD and AD there, but CD and CD is repeated, taking the place of x from our original equation. So in this case, the altitude is the geometric mean. So example 4, just kind of building off of this idea, is another way to figure out missing lengths using a geometric mean and using simplest radical form rather than decimals. So in this case, we have to use what we know, and we don't know both legs, but we do know hypotenuse and a leg. So our setup could be the length of the hypotenuse of triangle RPQ over the length of the hypotenuse of triangle RQS. That gives us 9 over y. And then on the other side, because y is on the bottom here, I know I need y on the top here. So that would be the length of the shorter leg in RPQ over the length of the shorter leg in RQS. Cross multiply 27 and y squared. So then the square root of 27 equals y. And simplest radical form means, can we pull a perfect square out of the square root of 27? Which the square root of 27 is the same thing as the square root of 9 times the square root of 3. And the square root of 9 is 3. So then we have 3 square roots of 3. Now, if you're confused on the geometric mean, don't worry, because the next 2 theorems are really the practical usage of it and making sense of why it matters. So theorem 7.6 is known as the geometric mean altitude theorem. So in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments. The length of the altitude is the geometric mean of the length of those two segments. So if we look at that diagram to the right, and that proportion underneath is what this theorem means. So that would end up being BD over CD equals CD over AD. So that's on top left and bottom right, the two parts of this segment. And then the altitude is the geometric mean in the bottom left and top right. For theorem 7.7, geometric mean leg theorem. So again, in a right triangle, the altitude from the right angle to the hypotenuse, so again, CD, divides the hypotenuse into two segments. So that would be those segments AD and segment DB. The length of each leg of the right triangle, so the length of each leg of the right triangle is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse that is adjacent, meaning next to the leg. So again, to make sense of that, see the diagram to the right. So in this case, AB being this whole hypotenuse over CB, which would be that piece, that leg right there. Then on the other one, CB over DB, CB being the hypotenuse, DB being that shorter adjacent leg that's attached to the hypotenuse. And if we look at the other triangles, AB, again, our hypotenuse, over AC, side adjacent to the hypotenuse, equals AC, our hypotenuse, over AD, the side adjacent to that hypotenuse. So the way we can use this is example 5, a rock climbing wall. To find the cost of installing a rock climbing wall in your school gymnasium, you need to find the height of the gym wall. You can use a cardboard square to line up the top and bottom of the gym wall. Your friend measures the vertical distance from the ground to your eye and the distance from you to the gym wall. Approximate the height of the gym wall, because we all know that's the most practical way you could ever measure a wall. So we're going to use theorem 7.6, and we know that 8.5 is the geometric mean of this part W and 5, because this 8.5 is our altitude, and as that 7.6, the geometric mean for the altitude tells us, it's the altitude of the two segments on the hypotenuse. So our setup in this case would be W over 8.5 equals 8.5 over 5. What we want to do then is cross multiply and divide, and W is approximately 14.5. So the height of our wall, we have to take the 5 feet we already knew, plus the 14.5 feet, and that gives us an approximate height of 19.5 feet.